So, which of these corners do you think is square? Who's for the top left dark red corner? Who's for the etc. etc. Now, only about X number of you got this correct. Why might that be? Any ideas? Well, the way I was kind of thinking about this was, it turns out that as humans, we find it very difficult to judge by eye what is and isn't square. And this kind of isn't surprising because in nature, at the macro scale, the scale of things that we see in our everyday life, there's actually no such thing as a perfect square. Squares are a human creation, and they're a very important creation that form the foundation of a lot of human developments. So, for example, this is an ancient Mesopotamian ziggurat, built in about 2300 BC. And ziggurats were the precursors of the pyramids. That means they are the things that came before the pyramids. And you can see how important it would have been for builders to be able to know what is and isn't square. So imagine if the builders started out maybe at this corner and they were building in this direction. And at the same time, another group of builders started out at this corner and they were building down this wall off into the distance here, directly into the page. What would happen if when they started, they didn't start off building completely square? When they got to the far corner, which would have been around here somewhere on the far side, what would have happened? Does anyone want to raise their hand and let me know what they think might have happened? Yeah, so, it wouldn't have matched up, it might have been really hard, they might have run into some problems. So, I guess the question from that is, how did these ancient Mesopotamians know, and Mesopotamians are kind of the people in the whole region, including Egypt, what we call nowadays Egypt. How did these ancient Mesopotamians know what was and what wasn't square, and if what they were building was square or not? I'm just going to read a little bit of text for you now. 4 is the length and 5 is the diagonal. What is the breadth? Its size is not known. 4 times 4 is 16. 5 times 5 is 25. You take 16 from 25 and there remains 9. What times what shall I take in order to get 9? 3 times 3 is 9. 3 is the breadth. So again, this is some text taken from an ancient Babylonian tablet, which is around the same area as the Egyptians as well. And that's a tablet is a big piece of stone that has things carved into it. So this was taken from an ancient Babylonian or ancient Egyptian tablet. And it comes from a time a bit after the Ziggurats that we were just looking at. So in terms of this, what were they talking about? Anyone want to raise a hand and share an idea? Well, it turns out that what they were talking about is a construction of a shape, something like this one. So you can see 4 is the length and 5 is the diagonal. What is the breadth? And they discovered that this 3 is the breadth. And it turns out that if you construct a triangle like this, of side lengths 3, 4, and hypotenuse 5, you'll always end up with a right-angled triangle. Now, considering this text here, is there anything that particularly strikes you about it? Anyone want to raise a hand and share an idea? Well, there are 2 things that struck me when I first read it. The first was that these people thought this idea was important enough for someone to bother to sit down with a hammer and chisel and carve this idea into stone, which we can imagine would have taken a long time. And the next thing that struck me was that this civilization obviously hadn't developed the mathematical formalisms, that is, the mathematical language that we use today. So instead of writing 4 squared, 4 with a small 2, as a superscript above it, to represent 4 times 4, they had to write out the word 4 times 4, which would have taken a lot longer and been a lot more annoying. So this combination 3, 4, 5 is only one of many combinations of side lengths that generate a right-angled triangle. So here's a list of more combinations. So we've got our 3, 4, 5 there, we've got our 5, 12, 13, 7, 24, 25, and all of these, this could represent the shorter side, this could represent the longer side, and there's our hypotenuse there. So these combinations are called Pythagorean triplets, and each of these combinations could have been used by the ancient Babylonians and Egyptians to construct things in ways that ensured that they were square. So, the moral of this story is that this idea of Pythagoras' theorem that we've heard so much about was known about well before Pythagoras was around. He was born around 571 years before the birth of Christ, and that ziggurat that we saw before, as I mentioned, was from 2,300 years before the birth of Christ. So here's a little cartoon that kind of captures that. We Egyptians first discovered the 3, 4, 5 right-angled triangle long before Pythagoras, and Pythagoras here says, I took the idea further and put my name to it, long before copyright laws. And so on the same topic, this is a picture of the Plimpton Tablet. So this is one of those tablets that I was mentioning before, stone with things carved into it. And the Plimpton Tablet is a special tablet. It's an ancient Babylonian tablet from around 1800 years before Christ. And what this tablet actually has on it, well, are there any guesses what this might be, given the topic of what we've been talking about today? Well, turns out these are exactly what we were looking at on the previous page. So these are sets of Pythagorean triplets. So we can guess or imagine that this would have been used by people, ancient builders, in the building of those amazing buildings like the Ziggurats and maybe even the pyramids. So, what have we looked at? Well, we looked at how it was hard to guess what is and what isn't square. We looked at how there's no such thing as squares in nature and they're a creation, and how the ancient Babylonians used the 3, 4, 5 relationship and other Pythagorean triplets long before the time of Pythagoras to construct the amazing buildings that they constructed. But today, we use the general form of Pythagoras' equation, which is this a squared plus b squared equals c squared. And this helps us to understand that the area of a square of side length given by the hypotenuse, so this square here, the area of this square is equal to the sum, adding together, of this square and this square, if we're looking at a right-angled triangle. So this here is an animation that I think captures that well and might help you to get a bit of a better feeling for Pythagoras' theorem. So, what just happened? What did we just see? Anyone want to raise their hand and share what they saw? And then you can ask other extension questions like, what's the difference between what we saw here and what we saw here? What are the similarities? What does this represent in here? And just kind of check for that understanding.